This instruction is on the constant stress beam. The purpose of the experiment is to confirm that the beam that we have has the geometry to cause it to be constant stress. It is not usual for a beam in bending to have constant stress along its shape. Notice that when you put a beam in bending, the amount of stress as you go away from the load is the lever arm gets larger, the amount of moment gets larger, therefore the amount of stress would get larger. But you can create the geometry to cause the amount of stress in the beam to remain constant if you do some algebra and relate the lever arm to the lever arm here in this case is going to be x as we move along the beam to the base of the beam, the dimension that's called the base of the beam. That algebra looks like this. If we write the amount of stress is m over s, the section modulus, this amount of moment is the force that we're applying, P, times the lever arm, in this case variable x. Substitute in the geometry for S, for the section modulus. That would give us this. And notice that if we cause x over b, b over x actually, to be a constant, k, then that will give us a constant amount of stress because this would be constant and the thickness would be constant. So as long as we relate, as long as we keep the base related to the lever arm constant, then it would give us a constant stress. In addition to that, we may need to know the amount of strain because the way we're going to approach this is actually with strain gauges, and if we have constant stress then we would have constant strain. Then the amount of strain, if you substitute the relationship for the modular elasticity, gives you this relationship for the amount of load as it's related to the amount of strain. Now the way we're going to use that is that we're going to build a beam. Notice too this relationship that allows us to calculate K if we simply know a base and an X value. So if we simply go along the beam, find an amount of distance along the beam, and the base at that location, we can calculate the constant for that shape, for that beam shape. Now, the way we're going to use this is the beam that we're furnished has two segments, segment A and segment B, and the way it was made, the geometry for this beam, assumes, or actually it was made so that the amount of stress or strain is constant in segment B but different from segment A. It is constant in segment A but different than segment B. And the way it was made is that the amount of constant stress or strain in A is two times that amount in B. And all we want to do is take some data and prove or disprove that beam geometry is actually valid. The way you're going to do that is that you're going to take two strain gauge readings in zone A, and those channels are the channels in the switch and balance unit that you will be using to read these strains. And we're going to take two strain gauge readings in zone B and get just the amount of strain, average those actually, and get the amount of strain in those two zones, and then calculate simply make a ratio, and we're assuming that the strain in A will be twice that in B. This should come out approximately equal to 2. and then calculate those constants that we mentioned, because we've measured some b's and x's in those two regions. Calculate those k's, and we assume this will be approximately 2. So you'll simply calculate those. If you use the homogeneous elasticity as 10.4 times 10 to the 6 psi, you will also be able to use this equation right here and calculate the amount of load that was applied. We didn't measure the amount of load, and those should be equal using the data from A and using the data from B, because we applied the same amount of load to get those strains.